Hello, Dan here from howtomechatronics.com, and in this video we will learn how to turn any DC motor into a standalone servo with a lot of features. Unlike regular servos that have limited motion of 180 or 270 degrees, this one has unlimited range of 360 degrees, and in addition to that we have the ability to adjust the range of rotation to whatever value we need. That's quite handy, I think, and on top of that we can even adjust the center point of the servo. So we can adjust both the center point and the range of rotation at the same time. Another feature is that we can adjust the sensitivity or how quickly the servo will respond to our input. Talking about the input, we can have three different input modes. We can control the servo with an analog voltage input or using a potentiometer. We can control the servo motor with an RC transmitter, as well as control the servo through a serial port by entering angle values through the serial monitor on our PC or laptop. We can also do that simultaneously, control the servo by entering values through the serial monitor and manually move the servo using the RC transmitter. The servo motor will know its current position at all times and we can see it on the serial monitor. On top of this servo motor features list is the continuous rotation mode. We can control and keep track of the servo motor position even in this continuous rotation mode. We can set the servo motor shaft to go to any position with an infinite number of turns. All of this is possible thanks to the 12-bit encoder this servo motor employs, the AS5600 magnetic rotary position sensor, and the implemented PID control for driving the DC motor. I made this custom servo motor control board, which includes its own microcontroller and everything else to easily turn any DC motor into a standalone servo motor. We just have to position the controller board at the center of the output shaft, including a specific magnet on the shaft, connect any size of DC motor with up to 3.5 amps rated current, power the whole system with 12 volts, and that's it. We get a servo motor from a normal DC motor with all these features. Now I will walk you through the entire process of making this custom built servo motor, so you can also make one on your own. I will explain the working principle of a servo motor, a closed loop controller, a PID controller, how I designed the custom PCB for it and the gearbox, as well as explain the code behind it. So we got quite a lot to cover, but before we do that, let's take a look at this video sponsor Onshape, which I also used for designing the gearbox for this custom built servo motor. Onshape is a cloud-native CAD plus PDM system used by businesses, and there is also a free version for at-home use. Believe it or not, Onshape was actually created by the founders of SolidWorks. With the rise of cloud computing, the SolidWorks founders realized that creating a CAD system from scratch in the cloud could create many new benefits that existing SolidWorks users can't experience. One benefit, for example, is that Onshape users are able to collaborate in real time, similar to how Google Docs works, which allows engineering and design teams to be more productive than ever. And you also no longer need to be concerned with who has the most recent version of a file, or checking a file in and out of an expensive and hard to manage PDM system. Onshape also works in a browser, which means it works across all operating systems and devices, including iOS and Android devices. Whether your company uses SolidWorks already and you are looking to modernize your engineering and design, or if you just want to try it out for at-home use, you can create a free Onshape account at onshape.pro/howtomechatronics. You can find the link in the description of the video. Thanks Onshape for sponsoring educational content like this. Back to topic, in order to explain the working principle of a servo motor, let's take apart a typical RC servo and see what's inside. We can notice that it has a small DC motor, a controller board, a potentiometer and 3 wires connection. 2 wires for the power and 1 for the input signal. Also, there are some gears for reducing the speed and increasing the torque of the DC motor. This is a typical setup for most RC or hobby servo motors. The potentiometer is attached to the output shaft of the DC motor and it acts as a position sensor. It tells the controller the current position of the servo motor shaft. The controller board controls the DC motor based on the input signal, the desired position, and the actual position that we get as feedback from the potentiometer. This represents a closed-loop control system. The input signal, or the desired position, is compared to the actual position of the motor that we get from the position feedback sensor. The difference that occurs, which is called the error, is then processed in the controller, which commands the motor to move until it reaches that desired position. So if we want to build our own servo motor with some bigger DC motors than these typical RC servos use, we can implement the same closed-loop control system. We just need a position sensor attached to the output shaft in some way and a microcontroller for driving the DC motor. Now, as for the position sensor, the simplest solution is to use a simple potentiometer just like the one we saw in the RC servos. The problem with these types of potentiometers though is that they have limited range of rotation of only 270 degrees, which directly limits the range of rotation of the servo motor. There are also other types of potentiometers that can make multiple turns and can provide better range and resolution, but still they have limited rotation. If we want the servo motor to have unlimited range of rotation, then we need to use an encoder. Encoders are electromechanical devices that can keep track of the angular position of the shaft with an unlimited rotation. There are many types of encoders like incremental or absolute, or depending on the sensing technology, optical, magnetic or capacitive. Of course, each of them has their own advantages and disadvantages, but more on that on the website article. I chose to use a magnetic encoder or the AS5600 magnetic rotary position sensor because it is very compact and easy to implement encoder, providing high precision or resolution. Just take a look at how small this microchip is. It has a built-in Hall effect sensor that can detect changes in the direction of the magnetic field. So we just have to attach a magnet to the output shaft of the motor and position it close to the microchip at a distance from 0.5 to 3 mm. Now as the rotor shaft and the magnet will rotate, the Hall effect sensor will capture those changes in the magnetic field direction. With the help of the built-in 12-bit analog to digital converter, the AS5600 sensor can output 4096 positions per turn or 360 degrees rotation. That means it can detect changes of the angular position as small as 0.0878 degrees. That's pretty impressive, and with the fact that it's very affordable and easy to get, I think it's the right choice for a custom built servo motor. Alright, so what else do we need? A microcontroller and a driver for the DC motor. I chose the AS5600 DC driver motor, which can handle up to 3.5 amps of current, and the Atmega 328 microcontroller. I chose the surface mount version of it as it's much more compact than the deep version, and my goal was to make as small as possible custom PCB on which I can include everything so that the servo motor can work as a standalone device. Here's the complete circuit diagram of this custom built servo motor. So we have the Atmega 328 microcontroller along with its recommended bare minimum circuit, which includes a 16 MHz oscillator, few capacitors and a resistor. For powering the microcontroller and the other components that require 5 volts, we are using the AMS1117 voltage regulator, which will drop the 12 volts power input to 5 volts. Here's the AS5600 position sensor with its recommended circuit, which includes 2 capacitors and 2 pull-up resistors for the I2C communication. The AS5600 DC motor driver needs just 1 resistor for limiting the current and 2 decoupling capacitors. Then we have the 2 potentiometers connected to the analog inputs of the microcontroller, one for adjusting the range of rotation and the other for adjusting the sensitivity of the servo. The push button is used for setting the center point of the servo, and a two-way dip switch for selecting the working modes of the servo. There's a pin header for the inputs of the servo, either analog voltage input or a digital PWM input from an RC receiver, along with a 5 volts and a ground pin. There's also a pin header for programming the microcontroller through the SPI protocol and the serial port. Here's a recap of this circuit and its workflow. So, the input or the desired angular position is received through these two pins. It can be either an analog voltage coming from a potentiometer or a digital PWM signal coming from an RC receiver. The input goes into the microcontroller, where it's compared to the actual angular position that is detected by the encoder, or the AS5600 position sensor. This sensor communicates with the microcontroller through the I2C protocol. Then the microcontroller does the math, it calculates the error, and according to it, it sends PWM signal to the DRV8871 driver, which drives the DC motor until it reaches that desired position. The whole circuit is powered by 12 volts, and the AS1117 voltage regulator provides 5 volts for the microcontroller and the other components appropriately. According to the circuit diagram, I tried to design a PCB as small as possible, and it came out to be 40 by 40 mm. I positioned the encoder at the bottom side and exactly at the center point of the PCB, so it can be easily mounted and aligned with the output shaft of the servo. All other components are located on the other side so that they won't interfere with the encoder and the output shaft. I ordered the PCB from PCBWay. Here we can simply upload the Gerber file, choose the properties for our PCB and order it at a reasonable price. I designed this PCB to have 4 layers, the middle ones are for ground, which increased the price a little bit. I didn't change any of the default properties except for the PCB color, which I chose to be blue. You can find and download the Gerber file for this PCB on the website article, or from the PCBWay project sharing community, through which you can also directly order the PCB. Nevertheless, after several days, the PCB arrived. The quality of the PCB is great and everything is exactly the same as in the design. Alright, so now we can move on with soldering the components to it. I started with the smaller components like this indicator LED and the capacitors and the resistors. This is actually my first time soldering these small SMD components and I was actually really bad at it. The most challenging was soldering the Atmega 328 microcontroller, as the pins are really small and very close to each other, but I somehow managed to do it. The AS5600 Encoder microchip was a bit easier to solder on the backside of the PCB, as well as the bigger through-hole components, like the dip switch, the potentiometers, the terminal blocks and the pin headers. Anyway, here's the final appearance of the controller board, which after all it turned out decent, I think. Now it's time to make a suitable gearbox for the DC motor and this microcontroller board. I designed the gearbox for this custom built servo motor using Onshape. The design of the gearbox depends on the DC motor, of course. As I mentioned, we can use any size DC motor in combination with this controller board we just made. Here I'm using a DC motor with 37mm diameter and a built-in gearbox that outputs 50 RPM. 50 RPM is a good speed for a servo motor, but I wanted to go a bit lower than that to get better torque, so I made a gearbox with 3 times speed reduction. I used herringbone gears for that purpose, as they are efficient and easy to make with a 3D printer. Of course, here we have the freedom to make this gearbox design however we want, as it depends on the DC motor that we want to use and what output speeds we want to get. I positioned the controller board on the backside of the gearbox and aligned it perfectly in the center of the output shaft. In case we want to use the DC motor shaft directly as an output, we can use a gear set with a ratio of 1:1 so that we can track the position of the shaft correctly. Or we could also use a belt system in such a case. Like I said, we have endless possibilities for making the gearbox. You can view and explore the 3D model of this custom built servo motor directly on your web browser with Onshape. The link to it is in the video description. Of course, you can also download the 3D model, as well as the STL files needed for 3D printing the parts on the website article. Okay, so here are the 3D printed parts for this build, so we can start assembling the servo motor now. Along with them we need some M3 bolts and threaded inserts and some bearings. First I secured the DC motor to the base plate with some M3 bolts with 8mm length. Then we can install the two gears in place. The smaller gear goes directly to the DC motor shaft and the bigger gear will be the output of the servo. Though the output shaft is composed of two parts. I installed threaded inserts on both sides of this output shaft part, on one side for connecting the gear to it and on the other side for attaching things on the output of the servo. I also installed threaded inserts to the smaller gear, which will be used for securing it to the DC motor shaft. Now we can slide the paired gears into their position. As these are herringbone gears, we must slide them both in place at the same time, otherwise we cannot pair them if we insert them one by one. Using a grab screw, I secured the small gear to the DC motor shaft. I applied 12 volts to the DC motor to check whether the gear set worked properly. We can finish the gearbox assembly by inserting the side panel, the ball bearing for the output shaft and the top cover. I installed some M3 threaded inserts on the back plate so we can secure the whole assembly with some 20mm long M3 bolts. I tested the gearbox again and it works great. We can notice how the output shaft rotates on the back side, and here we need to insert the magnet that the AS5600 encoder will keep track of. We can secure the controller board to the gearbox using some M2 bolts and nuts. The AS5600 position sensor is now perfectly aligned with the magnet, and so when the output shaft will rotate, it will measure the change in the magnetic field properly. Please note here that the magnetization direction of the permanent magnet is very important. Depending on whether it's axially or diametrically magnetized, we should position the magnet either perpendicular or parallel to the AS5600 IC. I ended up changing the direction of my magnet as it didn't have the right magnetization so that the AS5600 encoder could measure it. Next, I soldered two wires to the DC motor and connected the motor to the controller with the terminal block. As for the power, I connected two wires to the power terminal block, which on the other side have a DC power connector for connecting a 12 volts power supply. And that's it, our custom built servo motor is now done. What's left to do now is to give life to this servo, or program the controller. For that purpose, first we need to burn a bootloader to the Atmega 328 microcontroller. Without a bootloader, the microcontroller won't be able to understand the language or the code that we will send to it. To burn the bootloader to the Atmega 328 microcontroller, we need an Arduino board, and in my case, I will use an Arduino Nano board. We will use the SPI communication, so we need to connect the suitable SPI pins on the Arduino board to our controller board. Now, using the Arduino IDE, we need to open the Arduino ISP example sketch and upload it to the Arduino Nano board. With this code, the Arduino Nano is now capable of burning the bootloader to the Atmega 28 microcontroller. Next, from the Tools menu, as a programmer we need to select Arduino as ISP and then click Burn Bootloader. While burning the bootloader, we can notice that the Arduino Nano lights will blink a lot and that will result in a successful bootloader burn. Once we are done with that, now we can program or upload the code to the controller board with the help of an USB to UART interface module. The controller board has dedicated pins for easily connecting them, just like shown in this circuit diagram. Now we can open the code for this custom built servo motor that I made and upload it to the controller. Before we do that though, we should first install the libraries for the AS5600 sensor and the PID control. We can easily do that from the Arduino IDE library manager. Once we hit the upload button, the code will be written to our Atmega 328 controller through the USB to UART interface module. And that's it. Our custom built servo motor is now done. Now we can connect a potentiometer to it and test it out. Just a note that the analog input goes to the S pin on the controller board instead of the A pin. When designing the PCB, I have connected these two pins wrongly at the Atmega 328. Then we can select the analog input mode through the dip switch and power the servo, and here it is. We can control the servo motor position with the help of the analog input from the potentiometer. We have successfully converted our DC motor into a servo motor. We can also control the servo motor with the help of an RC transmitter. We just have to connect the RC receiver's signal pin from any channel to the A pin on the controller, and we can also use the 5 volts and ground pins for powering the RC receiver. The servo motor works perfectly. Like I mentioned at the beginning, it has few additional features than a typical RC servo. The range of rotation is not limited to 270 degrees, but it can move through all 360 degrees. Also, we can adjust the range of rotation of the servo. We can easily do that by adjusting the potentiometer on the controller. The range of rotation can be set to any value we need. With the other potentiometer, we can adjust the responsiveness of the servo or how quickly it responds to our input. It adjusts the value of the proportional component or the proportional gain of the PID controller. Of course, we can also adjust the other components of the PID controller, the integral and the derivative component in the code, and so we can get our servo motor respond the way we want. You can find more details about the PID controller on the website article. Anyway, in addition to that, we can also adjust the center point of the servo. There is a push button on the controller, and when we press it, it sets the current position of the servo motor as a new center point. So we can set the center point of the servo motor to whatever position we want, and it works in combination with the already mentioned feature, adjusting the range of rotation. There is one more feature, and that's the continuous rotation mode. In this mode, we can control the position of the servo motor with an infinite number of turns. The servo motor will always know its position. We can even control the servo through the serial port by entering angle values through the serial monitor on our PC or laptop. We can also do that simultaneously, control the servo motor by entering values through the serial monitor and manually move the servo using the RC transmitter. The servo motor will keep track of the position at all times. Now let's take a quick look at the code of this custom-built servo motor, and on the website article you will be able to find more details how it works as well as download it. So we start the loop by reading the encoder value or the current position of the shaft. Then if we are in the continuous rotation mode, we accept values from the serial monitor and use them as a set point or desired angle for the PID controller. If the input mode is set to potentiometer, we read the analog input and correct the set point value depending how far we turn it. We do the same set point correction if the input is the RC receiver. Here we convert the raw encoder values into angle values, and with these if statements we keep track in which quadrant the current position of the sensor is. With this information we keep track of how the shaft rotates and when it will make a full turn. The total angle is the input value for the PID controller. On the other hand, if we are in the limited rotation mode, first we read the potentiometer value, which is used for adjusting the range of rotation, and adjust the left and right limit of rotation accordingly. If the input mode is the potentiometer, we use its value as a set point value for the PID controller. If the input mode is the receiver, we read the incoming PWM value from the RC receiver and use that value as a set point. For setting a different center point, we check whether we have pressed the push button and capture that position as a new center point. According to it, then we have to adjust the actual readings from the encoder and offset them by the angle difference between the new and the old center point. We use that value as an input value for the PID controller. Using the analog input from the other potentiometer, we adjust the proportional gain of the PID controller, and finally we run the PID process to get the output value. We use that output value for driving the DC motors with PWM signal, left or right or in still position depending on the output value from the PID controller, or depending on the error between the desired and the actual position of the encoder reads. So that would be all for this video. Please note that the code is not well optimized and there is room for improvement. Also, If you try recreating this project, you should be prepared for troubleshoot. There are a lot of things that could go wrong, especially when soldering those small SMD components. I didn't get this servo motor working from the first try. Initially, I had some wrong connections on the PCB, then I ordered a new PCB again with new updates, but still needed few more tries to get it working. Nevertheless, I hope you enjoyed this video and learned something new so you can make something on your own. Don't forget to subscribe, and for more tutorials and projects, visit howtomechatronics.com.